questions or need anything before we get started today? Okay. And my main goal for today is to move on to some new material. Before that, though, just to make sure that the last couple things we talked about on Monday, excuse me, make sense in your brain. I'd like to very briefly review them before moving on. Last thing we talked about was the concept of angular momentum, the idea that if something is spinning, it has a certain amount of momentum that wants it to keep spinning at exactly the same rate in exactly the same axis, meaning if something is spinning clockwise about the z-axis, it wants to keep spinning clockwise around the z-axis. It doesn't want to suddenly become counterclockwise, and it doesn't want to change from one axis to another. It's try to keep spinning exactly the same way as it already is, and that is where you get gyroscopes from. Now, normal momentum is calculated with mass times velocity. Angular momentum is calculated with rotational inertia times rotational velocity. And if you can change your rotational inertia by, say, changing your radius, changing your mass distribution, angular momentum is still conserved and your angular velocity will change to make sure your angular momentum is the same from start to finish. Last time I demonstrated this by sitting in a stool, holding weights out as I spun, and then changing my moment of inertia, angular inertia. By pulling the weights in, angular inertia drops. My velocity had to rise in order to keep my momentum constant. So, very last rotational concept for now, to make sure that all that information feels good in your brain. Let's put some numbers to that specific situation. Consider me, with the two weights in my hands, as having a rotational inertia of 1. We're just going to call it 1 for simplicity's sake. So right now, like this, my rotational inertia is 1. And I start spinning at a rate of 1 rotation per second. When I pull my limbs in, let's say that my rotational inertia decreases to 0.5. It decreases because I'm drawing my mass closer to my center. It is easier to make me rotate. Based on the concept of conservation of angular momentum, when I do this, when I cut my rotational inertia in half, what is going to mathematically happen to my angular velocity?
Go double.
Double, very good. So if I was previously spinning at 1 rotation per second, what would it become? 2, precisely. Doubles from 1 to 2. So cut rotational inertia in half, your angular velocity will double. And again, this is the sort of thing figure skaters do when they pull their limbs in and start spinning very quickly in place. Now very quickly, just to test the inverse, let's say that somehow, magically, instead of pulling my limbs in, the weights I'm holding just become bigger. Like some wizard somehow defies reality and turns these from 1 kilogram apiece to like 10 kilograms apiece. That is going to decrease my moment of inertia from sorry, I said that backwards. That is going to increase my moment of inertia from 1 to 3, because now I have more mass further away from my axis of rotation. So, if somehow my moment of inertia magically increases to 3 instead of 1, what will happen to my rate of rotation? Go down. Very good. The angular momentum has to be conserved. And if somehow my moment of inertia became 3 instead of 1, what number would the 1 rotation per second become? Throughout these whole processes, my angular momentum must remain the same. Initially, we're multiplying 1 by 1. In the second scenario, we're multiplying 0.5 by 2. I cut my angular inertia in half, therefore my rotational velocity has to double to give you the same answer. If we instead increase my rotational inertia from 1 to 3, my rotational velocity is going to have to drop to 1/3 in order for the momentum to be the same. So I would begin spinning at 1/3 of a rotation per second. That all sound all right? Okay. Now with all that said, we are going to be setting rotation aside for a minute. We're not going to be completely done with it. One, rotation material will appear on the second test, so we should be working on the homework and keeping it in your brains. Now, officially, this course is based on a specific textbook. The order in which things are taught, the homework questions come out of a specific source book. And within that book, we have now finished up chapter 8, and then chapters 9 and 10 are about gravitational forces and how that causes orbit for the moon and other things in space. I'm actually choosing to skip that for the time being. I'm skipping that for the time being specifically because, one, I want to move on to what is within the book called chapters 11 and 12 so that we can start talking about matter and pressure and buoyancy. And two, I want to instead, I will cover gravity and how that math for the moon works, but I want to do it on eclipse day. Because if you aren't aware, on April 8th, there's going to be an eclipse. It's going to be really cool. We are not in the path of totality, but we are in a region where most of the sun will be blocked out on the afternoon of April 8th. So I'm planning a whole lesson that day and an alternative lab for that week. So that'll be the week that we do cover those sorts of things, gravity and orbit. I'm skipping past it for now so that we can discuss it on the day it's most relevant. Does that sound fair? Okay. So then for the time being, again, kind of keeping with the chapter numbers that the source book does use, we're going to skip past what is called 9 and 10 in that book for the time being and begin looking at what the book calls chapters 11, 12, and then towards next week, 13. This is the point. I mentioned sort of after test 1 that the second half of the course starts talking about weirder things. You know, we started with rotation, which is motion but weirder. And now we're going to be moving on to some even more different things that don't necessarily even involve motion. Because up till now, we've mostly been talking about motion. Either motion itself, displacement, velocity, acceleration, the force that causes motion, the energy you gain when you move or that you lose when you stop moving, different forms of motion. It's all been fairly motion-based up till now. And towards this latter end of the semester, we're going to talk about some different types of things, because I want to make sure that before the course ends, you have learned about pressure, waves, and electricity. Some things that are pretty important to life on Earth. Pressure describes a lot of physics concepts, and also air pressure keeps us alive. Waves are how you see and hear, and electricity, you know, powers the world. So those are things that I want to cover. And to facilitate that, what we're going to first talk about is some of the groundwork that will lead into those things. Because within physics, bless you. Well, first of all, any questions before I go into any of this new information? All right. So up till now, we've been talking mostly about motion, which is what happens when matter is moving. We haven't actually talked that much about the matter itself. We've just talked about stuff moving for the most part. Things exerting forces on each other and either moving because of it or not moving because of it. but we haven't focused that closely on the matter specifically. Matter being the stuff that makes up the entire universe. We've been measuring mass. You know, if I tell you that this is a 1 kilogram weight, that means that there is 1 kilogram worth of material contained within this hexagon. Before we move on, I want to make sure that you are familiar with matter itself, how matter works, so that we can then explain how that matter causes and reacts to the things that we will describe later on in this next month. And I'm expecting a lot of this of today to be a review. We're just kind of bringing back up the related concepts and making sure that you're familiar with them before we start moving on. So for today, we're talking about matter, and then Friday and into next week, we'll be talking about how matter starts reacting to and starts responding to specific things like pressure waves and electricity. Sound fair? All right, so to start with, matter, everything that has substance in the universe is made out of it. That includes solids, liquids, and gases. And all matter is made up of atoms, which are all made up of protons, neutrons, and electrons, the main subatomic particles. So again, I'm hoping that most of this is review. So all matter is made up of atoms. Protons and neutrons live in the nucleus. Electrons orbit around the nucleus. That means that the bulk of the atom, the bulk of mass in the universe, is made up of protons and neutrons, and the electrons detached from the nucleus just orbit it. Electrons are important because electricity is nothing but the electrons. So when we get to electricity, I'm going to be referring back to this because all electricity is either the motion of electrons or the lack of motion of electrons. So understanding the atom is important to more than just chemistry. Now these are the three particles that make up atoms, and therefore they make up everything. A brief review of the particles themselves. Protons are the positively charged ones. Proton for positive. They have a positive charge, and they have a teeny tiny amount of mass. That is times 10 to the negative 27th kilograms. Protons have about the same mass as neutrons. Neutrons are the blue ones in the center there. Technically, I would say neutrons are ever so slightly bigger, but you know, that extra amount of mass is really hard to measure. So it's fair to just say protons and neutrons have the same amount of mass. They're in the nucleus as well, and so therefore protons and neutrons combined make up the bulk of the mass of the atom and therefore the universe around us. Neutrons, as a reminder, have no charge. They are neutrally charged. They are not negatively charged. It's neutron for neutral. That confused me when I was first learning it, so just making it clear. Neutron for neutral. And they are both in the nucleus. Electrons are the negatively charged ones. They orbit around the electron. Note here, their charge is the same strength as protons, just negative instead of positive. And they have the teeniest, tiniest mass of known things in the universe. So here that's times 10 to the negative 31st. They are at least 1,000 times smaller than protons. They have the same strength of charge as protons, but like 1,000th the mass of protons. Because they're so much smaller, and because they are not fused into the nucleus, electrons are the things that can leave the atom, and that's why their motion is what forms electricity. Sound familiar so far? Just to check in. All right. Everything's made of atoms. The amount of protons, neutrons, and electrons in an atom determine what type of atom it is. Different types of atoms are called elements. We have the periodic table, which categorizes all of those elements. As a reminder, number of protons determines element, and so the number of protons correlates to the number of the element on the table. Hydrogen has 1 proton, so it's number 1. Helium has 2 protons, it's number 2, so on and so forth. Neutrons does not determine element. Neutrons determines isotope. If you have helium with 1 neutron, it's the same element as helium with 2 neutrons. It's just they have slightly different properties. They're still both helium. Neutrons doesn't determine elements, but it determines what flavor of that element you are dealing with. Hydrogen specifically has only 3 isotopes. There's hydrogen with no neutrons, hydrogen with 1 neutron, and hydrogen with 2 neutrons. And all 3 of those different flavors of hydrogen do slightly different things. But they're still all hydrogen. And then number of electrons only determines the charge of the atom, because protons are stuck in the nucleus. They may be positively charged, but they don't go anywhere. So you can't really remove a proton to change the charge of the atom very easily. Instead, if you want to change the charge of an atom, you have to move the electrons around. If it has more protons than electrons, it's more positively charged. And if it has more electrons than protons, it's more negatively charged. Things are only neutral if they have the same amount of protons and electrons. So most of the time, your body has equal amounts of both because you don't tend to have much of an electric charge. But if you build up a lot of static, it's because you've built up more electrons than you're supposed to have, and you shock yourself when you get rid of them. Or alternatively, you shock yourself when you touch something that has more electrons than it's supposed to. So again, electricity is the electrons. Electricity is technically negatively charged. Oh, good review. Any questions or objections? All right. Now this is not a chemistry class, so you don't have to memorize any sort of, you don't have to really memorize anything about the periodic table, but I do find it useful to still know how to use it. So I've made the table a little bit bigger here. Just out of practice, if an atom has 6 protons, what element is it based on this table? If you don't know what the letters stand for, you can just say the letters.
Carbon.
Carbon, very good. 6 protons is number 6, carbon, which is important. We are made of it. You find an atom with 8 protons and 6 neutrons, what element is it?
Oxygen.
Oxygen, very good. Protons determines element number, so we only care about that number, therefore number 8 is oxygen. Lastly, you find an atom with 11 protons, 12 neutrons, and 10 electrons. What is the sign of that atom's charge? Neutral, positive, or negative? Positive. Why is it positive? You're correct. Just want to know why.
More protons than electrons.
More protons than electrons. Very good. Again, protons are stuck in the nucleus, so you can't change charge by ripping those out. If you do, you set off an atom bomb. That's exaggeration, but so you have to change the charge by manipulating electrons. More protons than electrons means more positives than negatives, so net positive charge. That's called a cation. Negative ones are called anions. All right, very good. Questions before moving on? All right. Again, not a chemistry class, but it's still useful to know a few things about the periodic table in my opinion. So, small amount of information about the table itself. The columns are stacked in families, meaning that if things are in the same column, they are likely to have similar traits. That's not a guaranteed rule. For example, hydrogen is in its own family, and that family lives on top of the alkali metal family. Hydrogen's by itself. There's nothing else in the universe with the exact properties of hydrogen. So even though it's in the same column as these ones from lithium down, it doesn't have the same properties. Hydrogen is a combustible gas. Everything beneath it is an explosive metal that is solid at room temperature. And then there's these groups of families that kind of live on top of each other. Everything here in red is different to everything there in bluish purple. So it's more of a guideline that columns have similar properties than an absolute rule. But it is still good to know. For instance, the far right column is called the noble gases, helium down through Og. I don't actually know what that stands for. And those are unique in that they do nothing. They are gases that do nothing. They don't burn, they don't combust, they don't combine, they just exist. And in the case of helium, make your voice squeaky. Kind of on the opposite end of that, literally, on the other far side, everything in the far left column that isn't hydrogen is called an alkali metal, and they are famous for being metals that explode. Everything from lithium down blows up if you throw it into water. Frankly, you don't even have to throw it into water. The water in the air makes it start reacting. And that's why if you ever find raw elemental lithium, run. By the way, that's what's in the batteries. Don't throw batteries into water. That's why. And something that confused me when I was a kid, all of the abbreviations on here usually stand for the Latin name of the element. I always was confused about that until a chemistry teacher finally explained it to me. Some of them make sense in English, you know, C for carbon, O for oxygen, but iron is Fe because the Latin word for iron is ferrum. The Latin for silver is argentum, so it's Ag. The Latin for gold is aurum, that's why it's Au. And mercury's kind of weird because they use the Greek word for that. It's hydrargyrum or something to that effect, and that's why mercury is Hg. I always found that one the weirdest. Feel good so far? All right. My formatting's messed up. Dang it. There we go. Is that visible? That's better. All right, so elements and compounds are not the same thing. Elements have their own specific properties, but sometimes they combine to form things that have different properties. Elements by themselves have nothing else attached to them except optionally themselves. So since helium doesn't react with anything, you'll usually find helium in its pure elemental state. Sometimes you find raw iron in its elemental state. Hydrogen and oxygen usually bond to themselves. For instance, O2 is what you're breathing right now. You don't breathe pure oxygen, you breathe O2. But these are still considered pure elements even if they bond to themselves because there's no other type of atom attached to them. So it's still an element, but it's still we consider it a molecule if it's more than one atom. So molecules, elements can exist as either atoms or molecules, but compounds can only exist as molecules. It's like the squares and rectangles thing. All squares are rectangles, but not all rectangles are squares. So it's an element if there's only one type of atom present. It is a compound if there are multiple types of atom present. And compounds, pretty infamously, tend to have very different properties from the things that make them. Gotta fix my formatting again. So those are all elements. These are all compounds. And frankly, compounds are more common in nature than the elements because, you know, over however many years the Earth has been here, they've all reacted to something. So compounds always have more than one element, so more than one capital letter in their abbreviated forms, and they have very different properties from the things that make them. For example, CO2, this is what you exhale, is made out of one carbon and two oxygens. It's very different from both oxygen in that this will kill you if you're inhaling it, and it's very different from carbon in that carbon is usually solid at room temperature, and that's why we use it to make our bodies. This is rust, oxygen combined with iron. Iron is strong and oxygen keeps us alive, but rust is both flaky and poisonous. And then there's water, H2O, which hydrogen combusts and we breathe oxygen, but this is the liquid that we drink. So again, very different properties. I think probably the best example, I didn't actually list it here and I'm regretting that, is salt, sodium chloride. Sodium is on that far left column, which means that sodium by itself is explosive metal. And chlorine is the second, in the second to right column. That means it is a poisonous flammable gas. But somehow when you mix them together, you get rock salt. So, elements and compounds, not the same thing, have very different properties. Feeling good so far? All right, so, regardless of element or compound, this is now getting into the stuff that will segue into what we're covering Friday and next week. Whatever something is, element or compound, it's always going to exist in one of technically 5 states of matter, but we're just going to focus on these 4. And this is going to be the important part, because the state something is in is going to really affect how it reacts to pressure, which is our next big topic. In order of increasing temperature, matter tends to exist in solid at its coldest state, liquid at its next coldest state, gas as it warms up, and then plasma if you really warm it up. You're probably most familiar with the first 3, because those are the most common 3 that exist on this planet. But as it turns out, plasma is actually the most common state of matter in the entire universe, because stars and nebula are really hot, and the universe is mostly stars and nebula, not planets. So, stars are made of plasma, therefore the universe is mostly plasma. But on Earth, we mostly deal with solid, liquid, and gas. Important thing to note about solid, liquid, and gas: solids have definite shape and definite volume. This chunk of metal is a specific shape, and that is not going to spontaneously change by itself. This thing has been molded into this hexagonal cylinder, and that will not change on its own. External processes have to change its shape, and likewise, it would take an external process to change the volume of this object. If I wanted this to take up a different amount of space, I would have to manually crush it or rip it apart and reshape it myself. So solids have definite shape and definite volume. This is different to liquids and gases. Liquids have definite volume, but they don't have definite shape. Definite volume means a gallon of water will take up a gallon of space. Gallons are units of volume. But liquids don't have definite shape. You can pour that water into another container and it takes the shape of the new container. If I pour soda out of a 2-liter, it's not shaped like the 2-liter bottle anymore. So liquids do reshape themselves spontaneously, but they don't resize themselves spontaneously. They'll still take up a gallon of space. Gases, kind of ascending down this chain, gases have neither definite shape nor definite volume. Gases also take the shape of their container, but gases can change volume. You can compress a gas, and when you buy a helium tank at a party store, that tank is, a building's worth of helium forcibly compressed down into a tank this size. You can manipulate the volume of gases and the shape of gases, whereas neither liquids or solids, you can manipulate their volume very easily. For the purposes of this class, what this means is solids, since they don't change shape or volume by themselves, tend to be the things that pressure acts upon, and liquids and gases tend to be the things exerting pressure, because we tend to be submerged in them. You are submerged in gas right now because you live in an atmosphere. You are surrounded by gas at all times, and that gas, changes its shape constantly because you're moving through it. But liquids do the same thing. And so for the sake of this class, we are going to consider solids as something different to liquid and gas, which are both fluid. Since they can both flow, we consider both liquid and gas fluids. They have fluid properties, they both flow and change shape. Sound good? All right. Plasma is the fourth state of matter. There is secretly a fifth one, and it's kind of the inverse of plasma. Plasma is what happens if you take gas and make it hotter. The fifth one is called the Bose-Einstein condensate, which is a mouthful. And that's what happens if you take a solid and freeze it down to near absolute zero, in which case it starts getting timey-wimey for quantum reasons. But you'll never encounter that in nature, because absolute zero doesn't exist in nature. All right. I mentioned solids have definite volume, and we haven't done a whole lot with volume yet, so just to make sure you have that definition in your notes. Volume is the amount of three-dimensional space something takes up. The way to calculate something's volume just depends on the shape. If you ever need to know the volume of something, I will always tell you the formula of it. Some pretty common ones are currently on the board just for flavor. Got cube to the side, as long as it's a perfect cube, length times width times height, it should just be one number cubed, literally cubed. That's the reason we call it that. Cylinders have their own formula. Basically, you take the flat area of a circle and multiply it by the height. You're just building the cylinder up from the circle. And then spheres have their own variation of that formula. Again, you don't have to memorize any of these. I'm pretty sure some of these are in your formula sheet. If you ever need to calculate something's volume, you will have access to that formula. I just want to make sure that you understand that volume is not the same thing as surface area, which will become important as we start talking about pressure and how it interacts with surfaces. Volume and surface area are not the same thing. Volume is three-dimensional space taken up. Surface area is area, meaning two-dimensional space. So this cube its volume would be a cubed, length times width times height. But for a cube, all three of those things are the same thing. So a times a is a cubed. And that is the 3D space it takes up, literally length by width by height. And that tells you the cubed space. Surface area, though, is just the flat area of one or more sides of the surface. So the total surface area of this item, one face's flat area would be a times a, length times width, but this thing has 6 faces, right? Cubes have front side, other side, back side, top and bottom. And you'd have to add all of those together. So the surface area of the cube is 6 times the single flat area of one of its sides. The difference between these two things does matter to our future discussions of pressure and buoyancy, because the space something takes up affects how much fluid it will push apart, push away when you submerge it in a fluid, whereas surface area affects how much that pressure is able to act on the surface of that item. So I want to make sure the difference here is defined. Sound okay? All right. Questions before we apply this information, very briefly. Okay. So noting here this cube again, its dimensions are going to all be the same in each axis. Length, width, and height are all the same number. I want to compare the volume and surface area of this cube real quick. Let's say that this cube's length, width, and height are all 1 meter. So length times width times height. That's a pretty big cube, if I'm being honest, if you just envision that amount of space. Sorry. What would the volume of such a cube be? If a cube's sides are all 1 by 1 by 1, 1 cubed is 1 meter cubed. That would literally take up 1 cubic meter of space. So again, about this by this by this. Pretty big amount of space. That is different to the surface area of that cube, because that cube has 6 faces that are all 1 by 1. Again, the flat area of just one side is 1 by 1, and a cube has 6 of those things. So if the volume is 1 meter cubed, its total flat surface area is going to be 6 meters squared. It would take 6 1 by 1 sheets of paper to cover the whole surface of this cube. Sound good? Okay. Now, if you were to take this cube and throw it underwater, it would displace 1 cubic meter of water, which would be a certain number of gallons of water. And that water, fluids tend to exert pressure on things if you're submerged in them. So that fluid is now going to press on the cube, push into it to try to take its space back. And the water would then have this much flat area of cube surface to push against. Different sounding, okay? All right. Now, the difference, I feel, becomes more apparent when you start changing the size of the item. I want to kind of talk about the relationship between these two things. So we've got our 1 meter cubed cube. Let's say we build a second cube that is 2 meters by 2 meters by 2 meters, twice as big in every direction. So we go from this to this. Twice as big in every axis. What is its volume now? Eight. Very good. 2 times 2 times 2 is 8 meters cubed. So doubling its dimensions octupled the volume it takes up. Meanwhile, for its surface area, that would be 6 times 2 squared. I'll write out 2 times 2. What would that number be? Yeah, I heard someone say it. 24 meters squared. Note the difference in the unit there. So both increased. However, they did not increase at the same rate. Volume went from 1 to 8. That is literally a times 8 increase. Area went from 6 to 4, which is only times 4. the volume is growing faster than the surface area is. And then eventually, you have a cube whose sides are all 3 meters. So now we've tripled our dimensions. Volume, 3 cubed, that's 9 times 3 again, 36 meters cubed. The area, 6 times 3 times 3, so that's 9 times 6 is 56. 54, sorry. And now the volume is catching up even more. Thing I'd like to point out about this is, again, they aren't the same thing, volume and surface area. They don't increase at the same rate. And the bigger you make something, the exponentially bigger its volume gets in comparison to its surface area. This affects pressure, and it also affects, well, several things. I just wanted to point out the difference. The relationship between these two things is called the square cube law. Basically, as you double something's dimensions, surface area will quadruple, but volume will octuple. And this is ultimately the reason why Godzilla can't exist. Because the taller he gets, you know, if you take a dinosaur and multiply its dimensions by 100, its volume, therefore its mass, would increase by a factor of 10,000 for just being 100 times bigger. That makes it 10,000 times heavier, and then it's too heavy to survive. So this is why we don't have this fact, the difference in the growth rates of surface area and volume, is why we don't have giant animals, and also why we don't have giant robots. Same basic problem, they get too heavy. Questions? All right. We're doing a lot of talking today, and I want to check in. How you guys feeling? Okay. I feel like the last couple of lectures have been a lot of me talking about a lot of information very quickly. So again, feeling okay? All right. Last thing I'll just mention today, kind of referring back to elements and compounds really quickly, is a reminder that every different substance has a different density. Density refers to how much matter is contained within the volume of an item. It's literally mass divided by volume. So if you wanted to know the density of this object, you'd calculate its volume, you'd figure out its mass, and then you divide mass over volume. It's the rate of mass per volume. Unfortunately, someone decided to use the same letter for density as we use for momentum most of the time, rho. I'm going to try to call it density, like write the word density when I can help it, just to try to keep it straight, keep it separate. But the formula is density is mass over volume. It's a scalar, and it again defines how much stuff is contained within a certain volume of space. This again in reference to the square cube law we just talked about. If you make something twice as big, you octuple its volume. And according to density, every material has its own density. Iron always has the same density no matter how big the chunk of iron is. Water always has the same density no matter how big an amount of water you have. It tells you the amount of water within a certain volume. If you've got 1 kilogram of water, it takes up 1 meter cubed of space. Its density is 1 kilogram per meter cubed. If you increased your volume to 2 meters cubed, you'd have 2 kilograms of water. The density stays constant as long as it's the same type of material. Meaning that if you octuple something's volume by making it twice as big, you octuple its mass, meaning you also octuple its weight. And again, that's why we don't have giant animals and giant robots. You make something twice as big, it is 8 times as heavy, and then it can't support itself and it falls over. Make sense? Okay. We're going to be referring back to the density formula because we're going to factor in density when looking at, how different fluids create pressures. But we'll call it there for the day. Any last questions before we break? All right. Thank you all. Please let me know if you need anything. Report in the lab as normal. Please have a wonderful day.
Welcome.